In this episode, we build on classification thinking by looking at two closely related methods that often feel mysterious at first, even though their core idea is straightforward once you see it clearly. Linear discriminant analysis, LDA, and quadratic discriminant analysis, QDA, are classifiers that make strong assumptions about how data is distributed within each class, and those assumptions can be either a huge advantage or a painful weakness. Beginners sometimes avoid these models because they sound statistical, or they use them as a quick plug-in without understanding what they are betting on. The reality is that LDA and QDA can be excellent choices when their assumptions roughly match the world, especially when data is limited and you need a stable model that learns efficiently. They can also fail in very predictable ways when the assumptions are wrong, and that is what makes them useful to study, because the failures teach you how distribution and geometry influence classification. The goal is to understand what Gaussian assumptions mean, why LDA produces linear boundaries while QDA produces curved ones, and how to reason about when those models will help or hurt you. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. At a high level, both LDA and QDA are examples of generative classification, meaning they model how data is generated for each class and then use that to decide which class is most likely for a new point. That contrasts with methods like logistic regression, which focus directly on separating classes by modeling the probability of a label given inputs. The generative approach starts by assuming a shape for the distribution of features within each class, and the most common assumption here is that each class follows a multivariate Gaussian distribution. A multivariate Gaussian is the multi-feature version of a bell curve, defined by a mean vector, which tells you the center of the class, and a covariance matrix, which tells you the spread and how features vary together. Once you estimate those parameters from data, you can compute how likely a new point is under each class distribution, adjust by the class prior probabilities, and pick the class with the highest posterior probability. This can sound heavy, but conceptually it is just measuring how close a point is to each class center while also respecting the direction and shape of variation within that class. The reason LDA and QDA differ comes down to how they treat covariance, which is the pattern of how features spread and correlate. LDA assumes that all classes share the same covariance matrix, meaning each class is shaped the same way in feature space, even if their centers differ. This shared shape assumption is powerful because it reduces the number of parameters you need to estimate, which makes LDA more stable when you do not have a lot of training data. With shared covariance, the mathematics simplifies in a way that produces linear decision boundaries, meaning the dividing surface between classes is a hyperplane. You can picture it as slicing space with a flat sheet that separates regions where one class is more likely than another. QDA removes the shared covariance assumption and lets each class have its own covariance matrix, meaning each class can have its own shape and orientation. That flexibility leads to quadratic decision boundaries, which can curve, bend, and wrap around regions in a way that matches more complex class shapes. This difference in boundaries is the easiest mental handle for beginners because it connects directly to what the model can express. If two classes look like clouds of points that are roughly elliptical and similarly shaped, just shifted to different locations, then a linear boundary might be a natural fit and LDA can do well. If the classes have different spreads, such as one class being tight and concentrated while another is wide and diffuse, then a curved boundary might better capture where one becomes more likely than the other, and QDA can outperform LDA. However, more flexibility also means more risk of overfitting, especially when training data is limited. QDA must estimate a separate covariance matrix for each class, and covariance matrices have many parameters when there are many features. If you do not have enough examples, those estimates become noisy, and the resulting quadratic boundaries can become unstable and overly confident in weird regions. So the simple trade-off is stability versus flexibility, which is a theme you will see across many model families. Now let's focus on the Gaussian assumption itself and why it can help. When the assumption is roughly true, LDA and QDA make very efficient use of data because they are not trying to learn arbitrary boundaries from scratch. They are saying, in effect, each class is a bell-shaped blob, so we only need to learn where the blob is centered and how it spreads. This can be especially beneficial in small sample settings, where more flexible models struggle because they need many examples to learn complex patterns. The Gaussian assumption also supports smooth probability estimates because the likelihood functions are continuous and have a clear geometric interpretation. Another advantage is that these models can be computationally efficient and can work well as baselines for comparison. When you are learning, they are valuable because they show how distributional assumptions translate into boundaries, and that helps you reason about why certain data patterns are easier or harder to classify. But Gaussian assumptions can hurt when real data violates the bell curve idea in important ways. If class distributions are highly skewed, heavy-tailed, multimodal, or shaped like several clusters rather than one, then modeling them as a single Gaussian can be misleading. A class with two separate clusters, for example, will be poorly represented by one mean and one covariance, because the mean might land between the clusters in a region where no real points exist. The model will then assign high likelihood to an area that is not actually typical of that class, which can lead to systematic misclassification. Outliers can also cause problems because Gaussian-based likelihoods can be sensitive to extreme values, especially when those extremes distort covariance estimates. Another common issue is that real features might not have a natural continuous scale that fits a Gaussian, such as count data with many zeros or categorical encodings that are not truly numeric. In those cases, the Gaussian assumption is not just slightly off, it is a mismatch in the meaning of the data, and model behavior can become unpredictable. Understanding covariance more deeply helps you predict when things will go wrong. Covariance captures not only how wide each feature is, but also how features move together, and in real datasets, correlations can be strong, unstable, or driven by sampling artifacts. In LDA, the shared covariance matrix means the model believes the correlation pattern is the same for all classes, which can be false in settings where class membership changes behavior. If one class has strong correlation between two features and another class does not, forcing a shared covariance can blur the separation and reduce performance. In QDA, allowing separate covariance can fix that, but it also increases variance in the estimate, which means small training changes can swing the boundary. As a beginner, a helpful intuition is that LDA trusts a common notion of what typical variation looks like, while QDA allows each class to have its own notion of typical variation. That flexibility is not free, because each extra parameter is another opportunity to learn noise instead of signal. There is also a practical constraint that becomes important when the number of features is large compared to the number of examples. Covariance estimation becomes difficult in high dimensions, because you need enough data to estimate not just variances, but relationships between every pair of features. If you have many features, the covariance matrix can become poorly estimated, and in extreme cases it can become singular, meaning it cannot be inverted reliably, which the model needs for likelihood calculations. Even without diving into computation, the conceptual issue is that you cannot learn the shape of a blob in a high-dimensional space if you have only a handful of points. This is why dimensionality reduction, feature selection, or regularization often becomes important when applying these methods in practice. It also explains why LDA is often more forgiving than QDA in high-dimensional settings, because it estimates one shared covariance rather than one per class. Again, the theme is that assumptions can save you when data is scarce, but only if the assumptions are reasonable. Another subtle point is that LDA and QDA produce probabilistic outputs based on likelihoods and priors, and that makes class priors an important part of the story. If one class is much more common than another, the prior probability can shift the decision boundary, meaning the model will require stronger evidence to predict the rare class. This can be appropriate if the dataset reflects reality, but it can be misleading if your training set has been sampled in a way that changes the class proportions. Beginners sometimes evaluate performance on a balanced dataset and then deploy into an imbalanced environment, leading to unexpected behavior, especially in predicted probabilities. This connects back to calibration ideas, because a model can rank cases correctly but misstate probabilities if priors are not aligned with the real world. It also connects to stakeholder expectations, because people may interpret a low probability as a low risk, when it could simply reflect that the class is rare. Managing that requires clarity about base rates and how the model uses them, even when the model math is not presented. So how do you decide between LDA and QDA in a beginner-friendly way without turning it into a rule memorization exercise? One approach is to look at the data geometry you suspect. If you believe class clouds have similar shapes and your main need is a stable separator, LDA is a strong candidate. If you have evidence that class spreads differ meaningfully, such as one class being more variable or having different correlation patterns, QDA may capture that with curved boundaries. Then you layer in the data size question. If you have limited examples, QDA's flexibility may become a liability, and LDA may win even if its assumption is not perfect. If you have plenty of data, QDA can afford to estimate separate covariances more reliably and may outperform. The deeper skill is to treat these as hypotheses about class structure and then test which hypothesis fits better using careful evaluation, rather than assuming the more complex option is always better. Finally, it is valuable to connect LDA and QDA back to the broader model selection mindset for the CompTIA Data AI certification. These methods teach you that model choice is not only about power but about assumptions, and that assumptions are a form of prior knowledge you encode into the learning process. When Gaussian assumptions are roughly true, LDA and QDA can give you strong performance with simple, interpretable geometry and efficient learning. When those assumptions are wrong, they can produce confident errors that follow the shape of the mismatch, like drawing a neat ellipse around data that is actually two clusters. Recognizing those failure modes helps you avoid overclaiming and helps you explain results honestly to stakeholders who will use the model outputs. Most importantly, learning to ask when an assumption helps or hurts builds a habit of disciplined skepticism, where you do not just run a model and accept a score, but you reason about why it should work and how it might fail. That is what it means to use LDA and QDA appropriately, and it is a skill that carries into every other classifier you will learn.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.